All right. So we will continue our lectures on distribution theory. So let me recall our test functions first. So the test functions space. Okay. Function space d omega is equal to set of all c infinity functions d of omega with the support of v is compact. That's the whole thing. So the important development by Schwartz is giving an appropriate topology. That's a major thing. Giving a appropriate topology in d omega, and this is the major step. And then develop the calculus on its, so you need to have a correct locally convex type topology, which is what we are going to do it. Develop calculus on its dual space. That's what, if you look at the motivation, dual space d prime of omega, which should be quite big. So if you look at phi going to all these thing integral of f phi, the motivation which you have seen, this is linear continuity requires topology. So that's what we are looking at. It requires topology. Okay, and correct topology which we can do it. And so this association T actually is in the dual space. So we have to understand the calculus on the dual space, and that's what we are going to do it here. So I will give you the topology the more easiest way, but you can define via the as an inductive, which I will tell you. So let me give you the definition of topology. In terms of topology, I told you this is the most important thing to begin with. Topology in d omega. Okay. Because you have to take care of that boundary condition also. A sequence I will give in terms of the convergence, but you can also give a neighborhood systems and other things. Inductive limit topology. So there are it's a bit more hard work to exactly understand in terms of the locally convex topology. But giving this is enough for your regular working. A sequence phi n belongs to d omega is set to converge. So you have to understand very clearly this topology. Set to converge to phi in d omega. Okay, if there are two conditions, that is, one, there exists a compact set, compact K, contained in omega, such that support of all the functions is in the same compact set. Support of phi n is contained in K for all n. That's a it should be you already know that each phi n has a compact set, but that may vary from n to depending on the function. But we want a common compact set, so that support of phi n contained in for all n. And 2, all its derivative, d power alpha is a multi-index. So d power alpha of phi n, okay, d power alpha of pk converges to d power alpha of phi uniformly. Okay, whether it's you say that uniformity in K or omega doesn't matter because of the first condition, because outside K anyway d power alpha of E K is equal to 0. Okay, because there is no value, it's a 0 outside K uniformly. So whether you mention in the book on K or omega because of the condition 1, if that's not there, it is there. That is where the topology, there is a standard topology in C infinity, and that's not the topology which we are taking it. And the C infinity of omega topology is given by a family of semi-normed linear spaces, and this is not that topology. Okay, but that is used to get the systems and everything uniformly in K. Okay, and this should happen for all multi-index alpha, for all multi-index alpha. You can construct example. So as I said, I don't have time. This is only a kind of quick glimpse of that one. So your exercise, your study, construct examples. Of course, we can give plenty of examples, but I don't want to do it. Construct examples. See, if you look at it, my phi k of x is equal to 1 over n. This is not in the omega. Constant functions are not there. Okay, so you don't get constant functions are in the omega function. On the other hand, if I define something like say minus n to n, and if I take functions like say it's going like this, and it goes to 1 over n, then you can see that. But this this sequence, such sequences, this is over 1 over n, this height 1 over n. This phi n belongs to d omega. Okay, because it vanishes outside. But then, and this phi n of x converges to 0, and all its 0, phi n of x converges to 0 uniformly, you can see. But doesn't have a compact set. There is no common compact set. There is no fixed compact set. Okay, so you can get, say for example, this is up to, maybe you can very precisely construct up to minus 2n. This is up to minus n, and here you can construct such functions, n, this is 2n. So it will come down, that function sequence will converge very nicely, because phi n of x, and even if you take derivatives, all will can do that one, it will nicely come down. But then you don't have so you may get sequences which converges to C infinity uniformly. So the convergence here is not a C infinity convergence. Okay, so this convergence is, so that is why the construct examples more and more. So so CC infinity function, this is CC infinity, right? CC infinity together with the above, so whenever together with the above topology, together with the above topology is denoted by d omega. So when we use d omega, it is a point, a set wise d omega and CC infinity, d omega is the same as CC infinity of omega, set wise. Okay, so we use this notation when the above topology is given. So d omega is a very specific space. It is not just a set, it is a space with this topology. So some comments and remarks here. So I will not say a word, but if you want, you can read. This is an inductive limit topology. This is an inductive limit topology. In C infinity, you will get a semi-norm limit topology, and this topology is also a locally. This is important. It also gives a locally convex topology. It gives a locally convex topology. And this is important to have non-trivial d omega. This is a very, if you don't have a locally convex topology, this will be maybe empty. For example, you can define LP with P less than 1. We always study with LP with P greater than or equal to 1. The reason is that the dual is you don't get a good dual. Okay. So you look into such kind of thing. So if you don't have a proper locally convex, convex neighborhoods, local convex neighborhoods, the dual space may be empty. So, and you are looking at your dual space. Okay. It's a good topology. So you have a d prime of omega, and d prime is also complete. So that's also is a complete space. Okay. Is complete. The only small issue we will not face, so you have to be a little careful. Issue d of omega. D omega is not metrizable. So this is an important point you should be noting down. So these are all some remarks. So if you want to know more about this topology, you can look into the book of Rund, maybe K7. It's all given in our reference book. Okay, so you can see. Of course, these topologies are not mentioned in the book because the PDE book is not about the advanced topology. Okay, so this is a small inconvenience or small issue because you cannot take a metric to do this one. So that's a remark. With that, we are going to define we are almost defined definition distribution. D prime is the set of all continuous linear functionals. So let me recall, D prime of omega is the space of all continuous, a space of all continuous linear functionals on linear functionals. Okay, functionals on d omega. An element T, an element T in D prime is called a distribution. So D prime is the set of all called a distribution. Okay. So it's very clear about the distribution. So what is continuity? Continuity you have to understand properly. Okay. So there are two things. One is linearity. So there are two things. T belongs to D prime of omega. So let me write down the continuity also. If and only if one T from d omega to R is linear, 2 T is continuous. What is this? So continuous, that is T of phi k. This is what you have to verify all the time. T of phi k converges to T phi whenever phi k converges to phi in D. So to see this, so according to so that's a meeting. Whenever something converges in d omega, then corresponding T phi k converges to phi in D, then D phi k converges to T phi. And that's a natural continuity. Okay, the continuity in the domain should give you the convergence in the domain should give you the convergence there. So that is what the thing. So the thing is that you have to be carefully take this is the convergence in D. So we get, so that's a distribution. Okay, the thing is that, so let me use the other color. D prime itself is a topological space. Okay, D prime itself has a linear structure and a topology. Itself has a linear structure and topology. Structure and a topology inherited from topology inherited from D. So whenever you have a dual space, you can define a topology using the topologies from D. Okay, so what is a linear structure? That is T, if you have two elements T1, so you can define alpha T1 plus beta T2 acting at phi is equal to alpha T1 phi plus beta T2 phi. This is the definition T2 phi. Okay, for all T1 T2 in D prime anything, and of course phi is in D omega always. Okay, so we can actually show that it's a simple exercise. If you want, you can show that alpha T1 plus T2 beta T2 is D prime. That's a linear structure. So what is the topology? Topology on D prime. Topology on D prime. You need all this because for the analysis, because now you have to develop the calculus on D prime. Okay, Tk Tn converges to T in D prime, because when you are dealing with the PDE, you will see now solutions as distributions which are more objects. Okay, Tn converges to T whenever we say, so we say Tn converges to T whenever Tn of phi, that's what it inherited from phi, Tn of phi converges to T phi. These are real convergence because these are all real numbers. So you have a topology also here. Okay. So you have a topology. So T prime is also as a topological space with a convergence like that. Okay. And you can also see that D prime is complete. These are all some exercises or calculus with that is the Tn is in D prime. Tn converges to T. Okay, that means Tn of phi, that is Tn of phi converges to T of phi, that is Tn of phi converges to T phi for all phi in D omega. Okay, or more generally Tn of phi converges to, that is what we are going to do is that we are defining actually T phi. Suppose Tn is a sequence, suppose in the sense that, in this sense, limit of Tn of phi. That's the meaning of this. In this sense, I'm talking. Tn, if you then T is also the limit of a sequence is in D prime. Okay, so that's a sense I'm telling. In some sense, it's a complete space in this. T is a distribution. So you have all these very nice properties here which you can use it. Okay, so let me recall the examples. Okay, what are these examples? Recall the previous example. Okay, you have your f given by equal to mod x. Okay, and then what is your the correspondingly you have your Okay, it may not be example, maybe little later after this thing. So not now. So let me do the derivative now of a distribution. Okay. Okay, so we will do that. Okay, some more examples. Okay, f is locally integrable. Define Tf equal to phi equal to integral of Fe. So these are all exercises also. Fe, okay, for all v in d omega. So these examples, even if it is easy, please work out if you want to get a good understanding of that. Show that. Okay, Tf is in d prime. So you have to show linearity and continuity. Show linearity and continuity. So that implies every locally integrable function. So the class of all integrable function, locally integrable functions, so the class that's maybe L1 log if you wanted to. So the set of all locally integrable functions is contained in, can be identified with an element. So f can be, okay, in that sense. This is a distribution, this is a, that is f here in L1 log identified with, so always an identification, identified with Tf in d prime. And later, once you are comfortable with that, we will not use a separate notation f. So when f is an integrable, you also treat it as a distribution. It means that for every phi, integral of phi going to integral of phi is defined, and then it is continuous and linear. So we will not use in any distribution theory book or PDE book, you will not be using, you will not see that Tf is written again and again. That's only in the beginning f is identified with that. So whenever something is saying that an element here in a unique fashion identified with an element, not that two same thing will identify. And that's only thing always in maths you do this identification, we do it. So that's example one which you have seen. Okay, now let's go to the second example. Second example also, this example you have seen. Okay, define Tf, everything you verify. Tf of phi is equal to phi 0, which you have got it as a derivative of a thing, right? You got this as a with a minus sign probably. So Tf equal to phi 0, that's a Dirac delta basically. Okay, so this is a Dirac delta function. Tf is the Dirac delta function, and Tf equal to delta is the Dirac delta. So you see now a very clear mathematical definition of Dirac delta, which was doing because it's a Dirac delta. Because there many people get confused, it's a function. Dirac delta is not a function, and you have seen that this cannot be, this is Tf is not a locally, is not sorry, there is no, sorry, this is, okay, define T phi equal to phi 0. And this has a special notation, T is equal to Dirac delta is the Dirac delta. So this is by definition, this is delta phi. Whenever this is there, we use this notation. Okay. So we have seen earlier by exercise, delta is not generated by a, not generated by a locally integrable function. This is a new object by a locally integrable function. Hence, delta is a new object. Delta is a new object recovered from here. But then there are other ways of understanding Dirac delta. Indeed, delta can be defined via Radon measure. A measure which is finite on compact sets, which you may, in a measure theory, you would have studied them. In fact, you can define more distribution. Suppose mu is a, these are all examples. Suppose mu is a Radon measure. Radon measure, this is important because Radon measure is important because mu of k is finite for all compact k. In general, measures need not be finite for all compact k. Generally, when you define a measure, of course, Lebesgue measure is a Radon measure because it's finite on thing. But in general, the measures need not be finite on compact sets. So, set of all Radon measure define, so I can define a distribution. And measure is a bigger class than functions, right? So, using integrable, locally integrable or integrable functions, you can define measures. Okay, so but this is a new object, every measure. So the distribution theory consumes everything. So it has all kinds of objects which you are familiar with. So define your T mu acting at phi, you integrate phi d mu, not multiply mu. Okay, and this is finite because mu is, phi has a compact support, and hence this integral d phi is actually on a compact set because outside the compact set phi is 0. So these are the things you have to verify, and then this is finite and mu is finite. So verify. These are all the examples you have to verify. T mu is in D prime. So you see, so you have plenty of objects. Now let me give you a newer property other than that -1. Okay, so actually for D prime contains, so every Radon measure, so you can see that the class of Radon measures contained in D prime. And D prime omega contains more objects than measures. Contains more objects than measures. So here is another example. Define T acting at phi. Not earlier it defined for Dirac delta phi. Now I am defining acting at phi prime of 0. Okay. And the verify, that's easy. Verify T is in D prime. And the important example, T cannot be generated from a Radon measure. Cannot be generated by a Radon measure. That is, there does not exist any mu in M such that your T phi equal to phi prime of 0 is equal to integral of phi d mu. You cannot be written in a measure. So you have all kinds of objects and you also produce an object which is something new for in this measure theory, but these are all our objects used by the Dirac. In fact, phi prime is associated with the definition of a derivative. Now we are in before completing these lectures, we define what is called a weak derivative, and then we will stop here, and we will complete this with one more lecture. Initially we thought of completing in this lecture the whole thing, but I require one more lecture to do it. So for every distribution, let T is called a distribution now, an element, let D prime of omega, then you can derive. So you see, now I don't assume any smoothness or whatever it is. For every distribution I am going to define a distribution derivative. Then for any multi-index alpha, any multi-index alpha, define d power alpha of t. This is by definition d power alpha of t phi is equal to, by integrating, minus 1 power mod alpha. Mod alpha, you know that t acting at d. So you see how the smoothness of phi is used there. So your exercise show that d power alpha of t is also a distribution. So you see, for every distribution, so therefore the comment is that for every distribution, any amount of derivative can be defined. Derivatives can be defined for all orders. Derivatives can be defined of all orders. Of all orders. That's a very, very important thing. So with another comment, let me stop here with the whatever you see. So if f is equal to mod x, you already established that your df is g. This is the same derivative. The same thing matches with that. And when your fx is equal to hx, the Heaviside function, then your dh is equal to the Dirac delta, which we have defined. And you can also define with the delta is also a distribution, right? Now, so therefore the next exercise is that you can define d square of h, that is equal to d of delta, and so d of delta acting at phi, dh, h acting at phi, d delta x, you can easily see that it is phi prime of 0. You see, so this is actually a radon measure, but this is not even a measure. These are all called some dipole distribution used to be, not a measure. Okay. And then there is one more remark which I want to make it. Suppose f is, with this I will stop, f is locally integrable and f prime exists almost everywhere. F prime exists almost everywhere in a classical sense. So be careful when you are defining a classical sense and almost everywhere sense, almost classical sense. Then f prime need not be your distributional derivative. You need additional conditions in generally, need not be the distributional derivative. Distributional derivative. That you have seen already the example. For example, take f equal to h. Then h prime equal to 0 except at the origin. It is almost except at x equal to 0. But your distributional derivative dh is equal to delta. So you see, it's picking up that information. So the almost everywhere thing may not pick up your physics. And whenever you have a discontinuity like h, and that discontinuity you have a something derivative, that's what you are picking up. Picking up really the distributional derivative. So I will stop here, and then in the last class of this thing, we will give for a general PDE a concept of an L2. We have proven existence with necessary and sufficient condition for the general mth order equation and L2 solution quickly without all the proof, and then maybe briefly introduce Sobolev spaces to understand our weak formulation we have introduced in the first class of these weak solutions and how to prove that one. Thank you.